Once we know how much loading is being applied in plane to the diaphragm, determining how much of that load goes to each lateral load resisting element depends on whether the diaphragm is rigid or flexible. We cover rigid diaphragms in a later chapter. Here we are going to discuss how to analyze flexible diaphragms. Before we start, it would help to define what we mean by flexible and rigid diaphragms. Flexible diaphragms are much more flexible in plane than the lateral elements that support them. Metal deck roofs often behave this way, but it depends on the relative stiffnesses. Rigid diaphragms are much more stiff in plane than the lateral elements that support them. Cast-in-place concrete floors often behave this way, but again, it depends on the relative stiffnesses. The reality is that no diaphragm is perfectly flexible or perfectly rigid. All diaphragms are somewhere in between. But that means when we analyze a diaphragm as flexible and then as rigid, we have calculated the possible range of loads that each lateral element will experience due to a particular lateral load. For flexible diaphragms, we are going to assume that the diaphragm is perfectly flexible. That means we assume that the floor or roof diaphragm is infinitely more flexible in plane than the lateral load resisting elements that support it. So the diaphragm moves, but the lateral elements do not. Because of that assumption, we can idealize the diaphragm as a beam and each lateral element as a support. The result is called an equivalent beam model. If the diaphragm is only supported by two lateral elements in a direction, the equivalent beam model is determinate, and we can use equilibrium to find the reactions. The reactions represent the forces the lateral elements provide to the diaphragm. Therefore, we reverse the arrow to show the force that the diaphragm exerts on the lateral element. If the diaphragm is supported at 3 or more locations in a direction, the equivalent beam model is indeterminate. In later chapters, we will cover how to analyze indeterminate beams, but most of the time we make an approximation to deal with these cases. The approximation we typically make is to treat each panel of the diaphragm as acting independently. That means the equivalent beam model behaves simply supported between lateral elements and as a cantilever on ends that extend past the lateral elements. With this approximation, the segments are now determinate and we can find the reactions using equilibrium. Note that some lateral elements get loading from panels on two sides, so we add the reactions calculated from the left and right to obtain the net force on the lateral element. Performing this analysis at each diaphragm level gives us the point forces at all levels of the lateral elements. As a reminder, the final step in the analysis process is to add up these point forces and compare that total with the total applied load. If they don't match, we can be certain that we've made a mistake. Go back and fix it. In later chapters, we go over how to analyze the lateral elements given the point loads acting on them.